Hello everyone, and welcome to today's webinar hosted by the International Irradiation Association. My name is Arthur Dumba, and I'm the General Manager of the IIA. I will be your host today. We're happy to have presenters and attendees from around the world joining us, and we appreciate you taking the time to be here. I particularly welcome to IIA members joining us today. Your support makes events like this possible. All activities, including this webinar, are funded through membership. Before we get started, a quick introduction to the IIA. The International Irradiation Association is a not-for-profit association that supports the irradiation industry in its entirety, encompassing all technologies, applications, sectors, and stakeholder interests. We promote the safe and beneficial use of irradiation and act as a bridge between science and industry. The IIA works to communicate, educate, and advocate on behalf of our members, the global irradiation community. Membership with the IIA offers numerous benefits, including access to all our publications and resources, participation in our topical groups, working groups, visibility and promotional opportunities, and networking and collaboration with fellow members and our industry partners. You can learn more about the IIA's work on our website, iiaglobal.com. There you will find all of our initiatives and resources, as well as details on how membership can support your organization. If you have any questions, please do not hesitate to contact us at info@iia.com. Today's webinar is titled Radiation Dosimetry Now and in the Future. And we are joined by 4 expert presenters who will be sharing insights of chemical, optical, and physical dosimetry systems, their applications, limitations, and key selection factors, the challenges of dosimetry in low-energy electron beam and X-ray application, and emerging trends such as electron beam adoption, advanced training needs, release based on irradiation parameters, RBIP, and e-dosimetry via Monte Carlo modeling. The session will also introduce a single molecule dosimetry techniques that directly measure DNA damage, which can bridge between physical dosimetry and biological testing. A few housekeeping notes before we begin. The webinar is being recorded. A link to the recording will be shared with all participants shortly after the webinar is over. You can submit questions at any time using the Q&A function at the top of the screen. We will have a dedicated session for question and answers if we have time. We will endeavor to answer all your questions, but if we run out of time, we will circulate unanswered questions at a later date. The chat function has been turned off for the webinar, so please make sure to direct all your questions to the Q&A tab. Now over to our first presenter, Carl Scott Larson.
Hi, thank you, Arthur, for that introduction. This is talking about radiation dosimetry now and in the future. I'm mostly with the talking about what it is today. And so I'm going to give a current overview of the dosimetry systems that are in use in industry, and particularly focusing on mainly the ones that I'm most familiar with, which is the radiochromic systems and the alanine systems, but we'll touch on a few of the other systems that are out there. I've been working in the field for selling the radiochromic dosimetry systems for over 20 years, along with alanine. And so pretty familiar with that in the industry. So let's get into uses of dosimetry. Dosimetry is used to characterize equipment and to make sure that the dose delivered is what you want it to be under standardized conditions. It's used to establish your process, your minimums and maximums, and the dose distribution. And also it's used for routine monitoring to ensure that the delivered dose is within the specification that you need for your product or your process to get the effect that you want from your dosimetry for the radiation process on the product that you're using. So where is dosimetry used in industry? Looking at applications, one of the main categories, I kind of break them up into three categories, with the first being sterilization, generally of medical products and pharmaceuticals. This is quite a large industry user of dosimetry, as they use the radiation to sterilize multiple types of products. It does present challenges with the dosimeters themselves because there are homogeneous products, heterogeneous products, and different modalities used, X-ray, E-beam, and gamma, depending on what the product is and how that affects the product and whether the modality can produce the effect needed for that particular product. Along with that, you have with dosimeters that in with the product, you need to keep aware of spatial resolution, how that affects product. Can you use a dosimeter with that product in that modality? The second category that I have is food applications. There's pathogen elimination, shelf life extension, delayed ripening, disinfestation, and inhibition of sprouting are common areas that radiation processing is used. And with that, they need the dosimetry to verify that those processes are getting the correct dose. A lot of the food applications are more what we call on the low dose end of the scale. And so the types of dosimeters used or what type of dosimeter can be used will depend on the process, and you'll want to verify that that's applicable for your application. The third category that I have is treatments and modifications. This is a very wide industry, part of the industry. These processes can run the gamut from very low dose applications like curings of surface inks and resins to much higher dose applications like wire and cable treatment. There's industrial waste, polymer modification, vulcanization, curings and coatings, inks and resins, production of wire, heat shrinkable plastics, adhesives, lubricants, just many, many different types of products and processes. So in order to accommodate that, there are several types of dosimeters that have been used. And because there are different dose ranges and different modalities and different restrictions and places, even where they're processed, that can affect how the dosimetry system works and how effective it is. So there may be more than one system that's needed, or it may be you can use one system itself to accomplish what you do as a business. So there's a scale I found here, kind of gives you it from some very low doses of a few kilograms, such as in the seed stimulation mutation breeding for insects, up to a kind of a middle dose where you have your sterilization, to several kilogram doses for the industrial processes, and wanting to in the vulcanization tires, the hardness testing of semiconductors. There's a whole slew of different applications, and depending on what the application or applications are, you may want more than one type of dosimetry system. So the three main methods of dosimetry system is the calorimetric, which is measurement of temperature change. These are fairly large dosimeters, and we'll get into that in a little bit. There's the physical method dosimetry, where there's a physical change induced by ionization, such as with alanine, and the generation of free radicals to measure. And then the more chemical change, which is typically with a dye in some sort of plastic matrix as your dosimeter. So getting to some of the dosimeter types, we want the dosimeter to be independent of the output of the dosimetry equipment. That means we want the change in the dosimeter to be able to be measured quantitatively by an instrumentation to give a dose value that when the system is calibrated, it can give a good representation of what dose was delivered. And there's multiple types of dosimeters and what kind of outputs that they can do. There's the absorbance of light or radiochromic dosimeters, such as the Far West FWT60 film, which are the blue ones here at the top. There's the optical waveguides, which are tubes with a dye, generally in low-dose food applications. There's PMMA, which is a plastic with a dye in it. B3, which is another radiochromic film. These are the films are generally used quite a bit in electron beam processing because of their thinness. There is also the stable free radical measurement with EPR spectrometry and the alanine pellets. There is temperature change with a calorimeter, and then there's some chemical dosimeters such as Cirrus and dichromate that aren't necessarily used as much in the field anymore. A lot of it they have for reference because they are kind of a large size dosimeter. Trying to put in some applications may not work as well. And then there's some other TLD with emitted light intensity dosimeters. A lot of these are in badges that are probably most familiar with radiation processing, wearing those as your protection. Along with the dosimeters, you also have, you need to keep in mind what equipment and accessories. Each dosimeter system consists of the dosimeter, the reader to read out the value for the dosimeter, and then any other accessories. So for like a radiochromic, you'll need a spectrophotometer, photometer, a scanner, or densitometer to take the measurement. You may also need a thickness gauge to get the individual thickness of the dosimeter for a better measurement. There's gauge blocks for calibrating those thickness gauges. For calorimeters, there's the DVMs to measure resistance and temperature. There's thermometers, humidity meters, and the EPR spectrophotometers. Although those are all accessories, they need to be part of the system when you calibrate your system so that it's reflective of what you're doing in the situation that you're processing. So let's get quickly calorimeter. Calorimeters are generally a polystyrene and graphite and are commonly used in high energy electron beam. It's measuring that increase in temperature. Calorimeter systems are a fairly lower part of the range with about 0.1 kilogray to 50 kilograys. It uses a digital voltmeter along with the calorimeter to measure that temperature change. The cost of the calorimeters are fairly low, about $500 to $600 plus your voltmeter. So it's kind of an inexpensive system, but it does, for certain applications, it's very good, and also for um, testing with other routine dosimetry systems to verify that they are um, they're in calibration and reporting the dose as expected. Um, One of the other limitations is the dose gradients and other contributing influences when you're using a calorimeter need to be accounted for. One of the large main dosimeter systems being used is the alanine EPR system that uses a strong magnetic field to line up the spins of the unpaired electrons in stable free radical to create it in irradiation and separate the energy levels of those spins up and down. Microwaves are absorbed as electrons are promoted from the up-down spin. As you saw before, they could be in this pellets where they're single pellets loose, or there's also a tape tab configuration where the pellet is in the tab itself, and it is read with an EPR unit. The dose range of the alanine system is quite low, a few grays to up into 100 to 200 kilogray, depending on the alanine pellet. Again, it uses the EPR spectrophotometer. The cost of the system can be kind of high, um, somewhere between possibly 75 to 125,000 once you have the reader, the training, the accessories, the dosimeters. It can be quite more on the higher end scale as cost, but the alanine is a very good dosimeter. It's considered a type 1, so it can be used to uh, in transfer dosimetry systems. When you're calibrating, the national labs will often have an alanine dosimeter that's irradiated in situ with the routine system to establish the dose points. It can be used in high energy E-beam, gamma, and X-ray, so most modalities. And as I said, it comes in either bare pellet or a tape tab. There is in low energy E-beam some restriction due to the size of the dosimeter. The pellet itself may not be applicable. Um, Moving on to radiochromic system, those are the colored polymers that darken upon irradiation, and there's a few examples here on the slide. And the measurement is by passing a single white light wave. Usually you got your source goes through a lens where you get the specific wavelength of light that you want to go through your sample. The different radiochromic dosimeters use different wavelengths for their analysis, so you'd want to know from the manufacturer what that is. As an example, we have the Far West FWT60 film here that we make. From the unirradiated clear to a much higher dose, probably on the upper part of the scale, up to around 200 kilogray, and it varies in color. The B3 is a similar modality change, and so is the PMMA. They are all different types of radiochromic dosimeters. The range of radiochromic dosimeters in dose varies depending on what type of dosimeter product it is. There's some low dose ones, there's medium, and then a few of the films get up into the higher kilogray area. The cost of a system is in probably what I'd say a mid-range, anywhere from 5 to 75,000, depending on the type of spectrophotometer you use, if you need thickness gauges, and it's a little bit more flexible in for pricing. The radiochromos can be used in E-beam, gamma, and X-ray processing. But you do have to be aware of what the various dose ranges are. There are some limitations with size, even with these, depending on the modality, and there are humidity, sensitivity, and temperature to mitigate that a lot with the film dosimeters, at least, and even the PMMA. They'll be put into pouches for the customer so that they contain in an environment that is uniform. So quickly, when you're looking for a selection to select your dosimetry system, you'd want the dose range. What does the dosimeter measure in? The radiation type or modality. There's the influence quantities you want to keep in mind. Is it affected by temperature, humidity? Um, is there other UV that can affect that dosimeter? And how do you mitigate that in your system? There's the stability of the response of the dosimeter. How do you measure it? How is it stored? Do you need any post-radiation treatment? Some dosimeters require it, some do not. And what's the level of uncertainty you need within your system to have it as a good controlled system? And other things to keep in mind is the size of the dosimeter and the spatial resolution, of course, the cost and budget, and any training you need of your personnel to use that dosimetry system. To help you do some selection of what would work in your system, there are some ASTM standards, dosimetry standards on selecting, calibrating, uncertainty, the influence quantities for each dosimeter, and then on the individual dosimeter systems themselves. And these are the highlighted or bolded ones are ones that we've covered in this webinar. And they can be found with the ASTM website for more information. I would like to thank Far West Technology, Rotunda Scientific, GEX Corporation, Harwell Dosimeters, Steris, RISO, and IIA for sharing in this presentation. Thank you very much.
Thank you very much, Scott. Our next presenter is going to be Mark Bailey from the Danish Technical University. Mark?
Right, hello. I'll quickly switch my camera on so you can see me there. Hello, folks. And then I'll attempt to share my presentation screen, which is this one. So you should see the first slide of my presentation. I will now turn my camera off. And I'm just going to run through for a few minutes on low energy electrons and low energy X-rays, something on the applications and something on the dosimetry, building a little on what Scott has just talked about, but without actually repeating what he said, because I noticed that in his presentation he will be talking about dosimetry systems. So I'm not going to talk in detail about, for example, the alanine EPR system, other than what we can do with it. So I'm at, as Arthur just said, the Technical University of Denmark, in the research campus, which sticks out into Roskilde Fjord, just north of Roskilde in Denmark. The Center for Health Technology these days, and this is where we are, the little oval that's just appeared. Our offices are there. That's where I am, where Arne Miller is. Actually, he's probably in the next door office right now. And our colleague and manager, Christina Hankjegård, is also here. And the rest of the team, we're all here. Our labs are all here. We also have a laboratory for fundamental medical dosimetry, more the radiotherapy kind of end of things, and that's hiding over here in the buildings, just off the edge of the slide here. So that's where we are. That's who we are, and we actually have the Danish national standard for dose in a lab down here as well. So let's talk low energy electrons. The biggest application by far really is in things like surface treatments or cross-linking, and much of it is well, mainly in the cross-linking and curing of polymers. Many of the thin films that are made, and here you can see effectively a large bubble of film being blown, and then more layers can be added higher up in these kind of arrangements, so you can end up with multi-layer films which can then be cured with low energy electrons. And we're not really interested here in the surface dose in sterilization of devices or disinfection. You're really interested in bugs that sit on a surface. If they're in the bulk of the material, they don't really affect things that are happening when you touch them, when they're used on patients or in other types of situations or in contact with food. It's what's on the surface that counts there. But in this kind of application, we're interested in what's happening through the thickness. So it's more a question of how the material is affected by the radiation, and testing on the materials can then be done effectively independent of dosimeters. You may use dosimeters mostly in perhaps setting up the processes in your IQ, OQ processes, and then occasionally just confirming that things are as you expected. So here we have that situation where the films are being made, and here we have the situation where you can see that there's big rollers in place, and it goes through this large, wide, low energy irradiator. And I don't know if you can see it, but here is a fine adjustment tool here. It's a large hammer. Not quite sure what they used it for, but it did amuse us when we visited the place a few years ago. That's the biggest application. It's not the most critical application in many cases from where we sit, because if we're doing dosimetry, we really want to know can we do what's happening in the medical device or food packaging situation, and that does mean we want to know something about the surface dose. So in food and drink cartons, and a big example here is Tetra Pak. Not everything they do is irradiated. They still use other systems for surface treatment of their packaging material before it's folded and then filled and then sealed and then packaged for sending to the supermarkets. But they use typically a very low energy here, 80 keV electrons, which do not go very far in air. Right, we're only talking millimeters between their emitter and the surface of the material, and they can be processing tens of thousands of units an hour in one machine. And then these things appear in your supermarkets, and you will be very familiar with those kind of outputs. And they are very interested in the surface dose at that very low energy. And also, of course, in aseptic vaccine syringe filling lines or other pharmaceutical syringe filling lines, where you start with a tub of syringes, which will have been sterilized earlier in, say, a gamma process, or and then comes to the aseptic filling line system and is loaded into the system. And then in order to be filled, the tub has to not be in its outside packaging. The bag has to be removed. And the moment you do that, the tub is now no longer sterile in principle. It can come into contact with any floating bacterial spores that are around or other things. So the first thing that happens is it has to be processed by some low energy electrons. Low energy between typically 120 to 150 keV, maybe 200 keV in different manufacturers using slightly different geometries. But we want to make sure that the surface is treated, but that the electrons do not penetrate inside, because they don't want any ozone inside the tub interacting with adversely, perhaps with the vaccine or other pharmaceutical going into the syringes. So we have a low energy, say 120 keV on the top, which doesn't penetrate through the lid of the tub, which may be Tyvek, 1 or 2 layers or even 3 layers of Tyvek. And then from the bottom, you can go to a higher energy, because the thickness of the polystyrene or other polymer tub is thick enough that the electrons simply don't penetrate through it. I'll show something of that on the next slide. But you want to make sure that the dose reaches beyond the minimum dose they want, which is typically 25 kilogray, in the hard to reach corners. And the electrons here do not travel very far in air, even at 150 keV. So if we look at a little bit about that, here's a typical 150 keV beam in air situation. I modeled this a couple of years ago. It's using the XNRC Monte Carlo code. The beam comes into the air here, and it just spreads out, as you can see. And it with that real spread out situation, you can see that if you want to build up a dose in a particular location, and that location is any distance from the emitter, as we saw on the previous slide, then the tub is going to slowly build up that dose and then slowly see the dose finishing, and then of course part of the tub is shielding the thing from the other side. So you have to have a fairly big gap between tubs, and it can only run at a certain speed to make sure you get to that minimum dose, because we are all, as it were, victims of physics here, and at low energies it's a cloud, not a beam. So it's very tricky, and then of course we have other situations to think about. So with that, where are the minimum doses going to be, and how are we going to measure them? So here is where a minimum dose might be at a long distance from the emitter. Here is where a low dose might be, because it's partly shielded behind this vertical strut on the side of the tub. So how do we measure those? These are B3 films that we have carefully contoured around the interesting areas of the tub. There's a groove along here, so we use pieces of black rubber tube to push the dosimeter down into it so that we can actually get the contour right and see what the dose is like in that position. And of course, you can see that this doesn't really work with typical point dosimeters like the Far West or the GEX dose sticks or something. It's very difficult to place the dosimeter so that you will pick up a minimum dose. But with this kind of situation, you can then scan the dosimeter. So here is this kind of dosimeter scanned, and what you're seeing is that this area is hugely overdosed and is beyond the calibration of the dosimeter. This is using our research scan software on a scanned image, and then when you can see that there's a minimum dose region here, that if we look over here, you can see the shape of that profile, and we can see that it's about 20 kilogray, and that distance from this grid line to that grid line is 2 millimeters. So you have a very fine resolution if you need to get that resolution, and if you are trying to use a point dosimeter, it will be very difficult to actually get into that location and exactly place it. This is fairly typical for these kind of problems, and then of course we have to say, okay, how do we make that measurement traceable? Because of course we've just heard from Scott that that you can't use alanine pellets in this situation, and the B3 dosimeter is a pretty standard type 2 dosimeter. How do we get the dose? As we are interested in the surface dose, how do we get that? Particularly when we're looking at the depth dose distribution in water for a 125 keV beam being like this. This is 150 micrometers in water. It's not very deep. So at kind of 0.15 millimeters, it's a very thin distribution. Over here, you can see how we do a calibration type setup. We're using alanine films quite a lot. Now, they are currently not made, of course, by Kodak, but we have good supply. We have a supply now that's going to keep us going, we hope and expect, for probably more than 10 years now. So that's okay. But an alanine film is actually quite thick, and I'll demonstrate that in a moment. Otherwise, we can use that to confirm the calibration of recent B3 film and the B3 film that is actually part of the GEX dosimeter system. Their dose sticks and other dosimeters use the B3 film, so we can actually see what happens when we irradiate those, and then get the traceability back to the SI system, to the SI, because it's the Système International. You need to, so we can actually see what happens when we do that. But in order to do that, we have to relate this shape somehow to what we're seeing in the dosimeters, because with a thin B3 dosimeter, we can get nearly what's happening at the surface, which is what we might be interested in. But because it's a certain thickness, we're seeing a kind of averaging effect through the dosimeter. So this dosimeter does not actually tell you the dose at the surface unless you define the surface as being an 18 micrometer thick layer of B3, which is 20 micrometers or so of water. But if you use other dosimeters, say the Far West, you using the same kind of approach, you can see that the average dose might be a little lower. And please imagine, of course, if you're doing an 80 keV situation, then the depth dose curve you see will be right down here. And measuring the shape of the depth dose curve involves using a number of B3 dosimeters or a sheet of B3 and some steps placed on top of it that are even thinner, say 6 micrometers mylar steps, just to give you a series of points as you go down the depth dose curve. And here is the 135 or so micrometer alanine film, this film here. It's in water, that's about 180 micrometers. So the average dose that you would see if you calibrated it in a cobalt-60 beam or high energy electrons or whatever system you have, that would irradiate the whole film uniformly. But in the low energy situation, we're not getting a complete irradiation of the film. So the response is going to be much lower than it would be if the entire film received the same dose. So we have to look at this and use this information to arrive at the surface dose. And for the last, I guess, 15 years or more, we have used the d-mu formalism developed by Jakob Helt-Hansen when he was here at Risø High Dose Reference Laboratory, and Arne Miller and Peter Sharp at NPL, and another name or two that escapes my memory for the moment, to get a dose in a 1 micrometer water layer at the surface, and it's partially based on the extrapolation of the depth dose curve, and of course with correction factors for the irradiation temperature of the alanine, because alanine has a temperature variability, and the fact that the alanine calibration is not a straight line. So we have to actually remember that at the high doses near the surface, the alanine function may have bent over somewhat, but the lower depths doses lower down, it'll be nearly linear with dose. So we have to kind of back calculate to response, correct for temperature, forward calculate to dose again, and then we can apply everything to get the dose at the surface. It's slightly non-trivial, but and therefore it has a fairly big uncertainty at the moment, somewhat greater than 10% at k equals 2, which of course we are working to reduce, and watch this space for that as we go forward in time. Quickly then on low energy X-rays, only a couple of slides on this. Applications, I'm not going to talk about really anything other than a couple of applications. These are replacing cesium-137 sources. Cesium is not a nice source to have around. It's usually as a salt inside a sealed container. Cobalt-60 is a piece of cobalt, it's a piece of the metal, but in this case it's salt. So if you damage things and it comes into water, it can dissolve, and then you have a nasty cleanup operation. And that's been at the root of a number of accidents around the world over the decades. So these are being phased out in favor of X-ray sources, where the X-rays are generated deep inside the machine in the center of a tube, say here, and then whatever's being irradiated can be placed in locations around it and simply rotated around the source. And an exposure typically of a few hundred seconds will give the required dose. This device here on the left is used in the sterile insect technique, usually up to about 100 grays. Some insects it can take a few hundred grays for controlling insect pests of one sort or another, and hospital blood irradiators such as this machine on the right, because in some cases there can be graft versus host disease. It's not a blood type mismatch, it's simply graft versus host disease which affects some people. So a small dose is delivered to the blood, 25 to 50 grays, and the question then is, how do you measure that very low dose in X-rays and make that traceable again? And what we do with some of our, we work with some blood irradiators in hospitals. We provide a calibration service for that, and it takes alanine pellets And what we have to remember with alanine pellets is that the response of a dosimeter is quite different at low energy X-rays compared with cobalt-60 gamma rays. And so that means we then have to actually make a correction from what the calibration. We have a calibration in, say, cobalt-60 at the moment. We have the measurements in say, in this case, 125 keV. This is from a paper published 10 years ago. And the correction upwards can be quite significant. You can see that that is not a small 3% or 4% correction. In the case of measurements we make with 155 kV X-rays in blood irradiators, we can apply a correction of up to 19%. Again, the uncertainty is approaching 6% at K equals 2. It's a slightly non-trivial set of measurements, and we have to deeply understand what's going on inside the dosimeter. And work happened here just a few years ago with my former colleague Jakob Purengor, who left us actually only a few months ago to go on to other things. But it's something that we do here quite a lot. So that's that. And I believe that's actually my last slide. So I hope that was of some interest to everyone, and we can deal with anything that arises in questions afterwards or later. So there you go, and thank you very much.
Thank you very much, Mark. Our next presenter is Florent from Ariel.
Okay, can you hear me loud and clear?
Yes, we can hear you.
Okay, thank you. Hi, everyone. So let me put my camera. We are now going to discuss about the future. And I want to share with you a few evolutions that may happen, may not happen, but ideas about the digital path of dosimetry. So usually I say we have to dream if we want to innovate. So stay with me, dream a little bit, but we have to keep our, how we say in France, keep our feet on earth, on the ground, however. So in the last, why this does not work? Now, actually, I like this picture, this nice Lichtenberg tree we did years ago. And it depicts the applications we have covered already, or Scott did cover. In the last decade, let's say, and during the pandemic, there was a kind of, and after the pandemic, there was a kind of shift of technology. And we went from cobalt-60, cesium, as Mark just mentioned, to machine sources. And this is ongoing, this change is ongoing. And now all these applications can be done with machine sources, high energy X-ray, high energy E-beam, low energy E-beam, lower energy E-beam, etc. And why don't we take advantage of this shift or this move to change the paradigm? Why don't we adopt new methods, especially for E-beam and X-ray? The first one I want to mention very rapidly here is RBIP. And if you go to this to the Irradiation panel website, you can download a recent publication about it's an introductory document we have released a few weeks ago about RBIP. And of course, other documents much more technical for implementation of RBIP will be worked on and published. RBIP uses a model. So this means that it is only a model which has to reflect the reality. The second thing is Monte Carlo simulation. It can be used for multiple applications, the design of product packaging, OQ, to better understand the process or optimize the process. PQ, for E-beam, it's really interesting to do PQ with modeling because it helps you to locate minimum dose, maximum dose. You can optimize the UR, etc. We can We'll see an example later on. And why not calculating an absolute dose? I'm not speaking now about traceability. I don't know what is traceability with the simulation, with the simulated dose, but maybe because current uncertainty is 3–5%, k equal 2, depending on the class of dosimeter, the type of dosimeter, maybe, I don't know, maybe we can do better. And then why not speak and use simulation to do primary dosimetry? That means use simulation to do calibrations, for example. So these are big question marks. Huh? In the wheel of the irradiation process, we have these different steps, and everything is linked to traceable dosimetry. Traceable dosimetry systems, traceable to, as Marc said, to the BIPM, Bureau International des Poids et Mesures. And with these tools, we can do IQ, OQ, PQ, the routine process control, the release, and maintaining the process. Now, with what I said, maybe the evolution is going to be e-dosimetry. Maybe we can have reduced uncertainties. Let's see. We can use OQ, simulation for OQ, simulation for PQ, defining the UR, the locations, as I mentioned. RBIP is somehow already applied by some of the players. It has to be documented, more guidance given in order to spread this out. But today, we still need a physical dosimeter for releasing the product. And even with RBIP, sometimes you have to connect between the calculated, the virtual dose, and the physical dosimeter, because again, RBIP uses this model, very simple, should be linear, must be linear, but it is a model. So in all these tasks here in gray, we can imagine some use of simulation or models. What is needed upfront? This is very important. Of course, we need accurate input data. For RBIP, for example, we need to know the current, the beam width, the velocity of the conveyor. Of course, simulation also, we need to know the energy spectrum, more than the energy of the radiation, the energy spectrum. We need to be able to model the radiation geometry, the volt, the product, the target when it comes to X-ray. So some of these important data are common to RBIP and simulation. And I think that if we want to do better simulations, better modeling, we have to develop tools to monitor and maybe to control the irradiators with output parameters, with real measurement of output parameters. A little bit how they do, like they do in the pharma world with their PAT, process analytical technologies. So if this could be integrated, we would have real measurements of some parameters which are today indirectly measured or calculated, which implies a risk when we do the modeling. An example, IBA has developed the X-ray flux monitor. It has been developed actually with us, with IRIAL, and there are some papers on it. This is one way of doing PAT in our facilities. When it comes to simulation, use CT images to model realistic products and model variabilities, which cannot be seen with CAD files, for example. And then maybe in order to mitigate the risk again, but currently we already have faced this kind of risk. In order to make sure that the processed product under the beams or in the radiation field is the one we have actually PQ'd, maybe inline imaging will be necessary. So these are the needs up front. Coming to modeling, there are many modeling softwares. What I usually say, choose one, choose yours, qualify, validate it according to what you to your use and to your expectations. And of course, all softwares, all tools may not be optimal for all kind of radiation types and energy. Using the simulation tools, actually, we need confidence in these results. And the question I was asking myself, why shouldn't we believe in the results? Why can simulated results be wrong or inaccurate? There are many reasons. Input data, we already mentioned. The cross sections, the interaction parameters. Particle tracking. How far are we going to track the particle to become more precise? How can we analyze the results? All this, for all to answer all these questions and make sure that all this information and data is correctly mastered, we need documentation, we need guidance, we need training, of course, to make the user of these tools to gain competency to them for the use of the modeling tools. An example here is the cutoff, energy cutoff. You see that in this slide, we have 4 or 5 different energy cutoffs. This is an example of gate, Géant 4 actually. A gate is the front thing. So here you see that when we choose a cutoff from 1 kV or 100 kV, which makes the thing much faster, 100 kV, because we track the particle much less. You see that the results are not the same. This is a simple depth dose distribution in a polystyrene block. And the results can be significantly different in terms of slope of the curve, in terms of extrapolated range. Another way to analyze or to evaluate the tools is the efficiency, epsilon. It's a combination of the uncertainty and the time, the computational time when you launch a simulation. And we have got some results with GATE, and we have got some results through Frédéric Tessier at NRC, showing that for this application, high energy electrons, something which is well known, X is more efficient than GATE or Géant 4. There is a publication in preparation about the comparison of different tools, by the way. So examples where, or one example where the use is straightforward without any question about the accuracy, etc. One example I want to show you here. The use of scattering plate. Can we simulate the use of scattering plate versus no scattering plate of a product being scanned? This is the CT scan of a product with 2 boxes inside, double-side irradiation without scattering plate, DUR 1.99, and you already see in my slide the DUR with the scattering plate, which is coming now, DUR 1.39. Of course, these values may not be the truth, may not be very accurate, but at least we show here, without any question, that with scattering plate, the DUR is much better than without. It is more complicated when we want to compare simulation results with physical dosimetry. And here is the example. Sorry, I always show this one because We don't have many examples we can show, we are allowed to show and to share with everyone. This is the STERI test, which was CT scanned with a given resolution. So it's a box of 30 by 30 by 30 centimeters, CT scanned, irradiated from both sides with 10 MeV electrons, and you see in the product where are the minimums, the maximum dose zones, maximum in red, minimum in blue, which is a very good help to position the PQ dose mapping dosimeters and to calculate the DUR. So if you compare with the measurement, you find DUR with the Monte Carlo simulation 1.992, experiment with FWT dosimeters 1.93. Great. But is it a good agreement? Are these values similar? Actually, we don't know. We have to compare them. And for this, we have to use a way of comparison. We use typically the EN calculation, very simple, but we have to know the uncertainties on both of the dose measured and simulated. And this is where the questions come. How do we estimate the uncertainties for a simulated dose? There are some other examples which have been shown already, shared with you through the IIA. One is, there is a video on the website from March 25, which gives some examples. And in March 24, there was a presentation by IBA, Trad, and Sartorius on a product. We have PQ dose mapped at aerial, irradiated with X-ray in real, and then simulated and compared. So many questions to be answered, many questions if we go towards using simulation tools instead of physical dosimetry. Simulations, what about the accuracy of the input data we measure? We already mentioned this. Do we know the energy spectrum? We can simulate it, but we don't actually have the tools to measure it. It's really important. Beam width, beam length, okay, we have an indirect measurement. But what about beam uniformity? The beam is not flat like this. There are some variations. If we don't have any information about these variations, we cannot do good simulations. How far can we have, do we have to follow particles? If we irradiate with X-ray, can we model Kerma water? Can we calculate Kerma water or dose to water? There will be a discrepancy, but maybe it's good enough. And again, what do we know about uncertainty? We need to know this uncertainty in order to claim similarity between a physical measurement and simulated. Where do we have to measure? Are we going to measure and compare the dose in 2 dosimeters? It might be important in order to validate the tools, in order to validate the input information, etc. Why not? But normally, the minimum dose in a product should be determined in the zones where the microorganisms can live. So at the surface of the medical device, or maybe in the flesh if there is a certain porosity. Maximum dose will be probably in the flesh of the material because it's a question of material compatibility with the irradiation dose. If we use CT scan images, what resolution is needed? Which resolution is needed? How can we differentiate the different material components in the product? Do we need a reference material to be able to do this segmentation? And again, it might be necessary to scan the product with dosimeters for acceptance or validation purposes. We need these answers. We need to answer these questions. but we have to make sure that these answers are in line with our history. This industry does radiation sterilization and other applications for decades, 5-6 decades, with success and be very efficient. So we cannot, because we want to use a new tool, we cannot go be negative or counter an existing process. We need guidance documents. I mentioned this. The STM has IAEA, sorry, has the panel is also, the irradiation panel is also going to work on documents. And luckily, 2 weeks ago, we had a scientific exchange on the topic of modeling organized by KERMS at NIST. And the idea of a group of experts was launched with precise objectives and action plan in order to see how we can implement modeling. And of course, we need adopters, early adopters. We need somebody and organizations and users of the irradiation technology to create examples, to build examples, to submit these to the regulators, because finally we will have to gain the regulators' acceptance. So that's it. If you can dream it, you can do it. If we can dream it, we can do it. Maybe, maybe not. Thank you, AA again, and thanks to my colleagues, Lena, Thomas, Abbas, Nicolas, and my boss. Don't forget your boss, Alain. Yeah, because through him, I'm here today, and we are working on these very, very exciting topics about digital dosimetry. Thank you.
Thank you, Florent. We're running a bit over time, but please stay with us. Our final presenter is Joseph Robertson from the National Institute of Standards and Technology, NIST.
Well, thank everybody for sticking around for this. I really appreciated Florent's talk because it bridges very nicely into what I want to show everybody today. And this is actually going to be more about work that's going on right now in my laboratory and the Radiation Physics Division at NIST. And our goal is really to build in new measurement systems that can support existing needs for sterilization and other dosimetry measures. So we're talking a little bit about, building up a system where we can start proposing things that lead to parametric release for products, and that's really built on two principles: the physical dosimetry, which is a surrogate infer microbial inactivation, and also really the core is microbial testing. You really, the goal is to get rid of the bacteria and viruses that will cause downstream problems. And there's no other way of doing that right now than actually growing the microbes and looking to see what's there. Of course, this is supported in great detail with modeling and new ability that we're coming up with in computer systems and computational systems. But we have to tie these together in order to meet the needs of pending regulations and other features. And we're proposing at NIST to do this through biodosimetry. And I'm going to talk about one measurement that we're developing here that is a tool that I believe can bridge the physical dosimetry and the microbial testing to give us better confidence in all of these systems going forward. So the biodosimetry is a bridge between physical dosimetry and microbiology, and the goal is to unify and strengthen rationale for parametric release. So what are we needing to do? So for sterility assurance, we have physical dosimetry, which is really the measure of absorbed dose. This is energy deposited into the material. It's really a step removed from the true goal, which is the destruction of the microbes on the surface. Makes a lot of assumptions, adds to tremendous uncertainty, and requires being very conservative with your processing conditions to maintain safety. And it does not measure biological effect. Microbiology is great. You can directly measure the biological effect. It's the gold standard for sterility, but it's slow. It can take days to weeks. It's resource intensive, and it's impractical for product release just because of the cost and the extra requirements you would need to maintain a microbe or a biochemistry lab on site. And it's not ideal for continuous process monitoring. So the measurements that we're developing at NIST are really a biodosimetric approach to sterility assurance. What we're doing is quantifying DNA damage using a direct nanopore-based analysis system. I'll show you a little bit about what that is later. This acts as a high-resolution proxy for microbial inactivation. We're measuring the damage to the microbes' genomes directly. And so we can determine what's been destroyed from the surface, for instance, just by looking at fragmentation patterns of the nucleic acids in those bacteria. Should provide an accurate estimate for log reduction, the kill value, and it bridges that gap between physical dosimetry and microbiological outcomes. And it brings us a step closer to the biological foundation, what the actual core problem that we're trying to solve is in this system. Now, just a really brief step back into what ionizing radiation measurements are. You've obviously seen several talks that describe this, but right now what we measure is dose. And the other thing that we measure is the biological effect. And these two things are useful, neither of which is exactly is quick or easy to do. But between these two measurements, we have all kinds of details about the chemical and biological damage. And that depends, as you've seen, on the radiation type, tissue, cellular environment, depth, environmental factors, water content, and microbial load. And what I'm proposing here is that if we directly measure the DNA, we're getting to the source of this measurement, the source of the measurement needs, with much less intense measurement requirements than what you would need with either dose alone or the biological effects measured through culture. Now, how is DNA damaged in radiation? Because obviously we're talking about X-rays and electron beams here. We have different sources of radiation, and those interact with DNA slightly differently. All of these radiation sources in the presence of water create radical oxide species, which directly attack DNA. Low LET radiation, which electron beams would fall into, deposit their energy slightly differently into the system. And of course, high LET particles deposit more energy. And what you can see is from these cartoons is the different radiation sources should interact with the DNA differently. And I'm telling you, or I'm suggesting here, that we can measure these differences with a relatively inexpensive, easy to implement technology. And of course, what we want to do is tie dose to microbial load, and I'm telling you that we can do this through measuring DNA damage. The measurement that we're developing is a resistive pulse sensor, classified as a nanopore sensor, and the measurement is simple. What you do is you take a small aperture that's nanometers in scale. So this is on the order of the size of a DNA molecule. This can be fabricated in a fab. It can be made in laboratory scale with simple equipment. But the point or the purpose here is that you have two solution compartments that are separated by an aperture that is between 10 and 20 nanometers in diameter. If you apply a sample that contains DNA on one side and a voltage across that membrane, you drive the DNA into the pore, and every time the molecule partitions into the pore, you see a resistive pulse. So we're counting molecules as traced at the top of the screen. Each of those downward spikes is one molecule going through the pore. By decoding these pulses, integrating the charge across those resistive pulses, we can build out a spectrogram that gives you the size distribution of the nucleic acids with very high fidelity. So this is an extremely inexpensive, easy to implement measurement. And then we can take this and we can test it with irradiated sources or irradiated systems. So this is an early experiment that we did in my lab where we exposed a standard DNA molecule from 0 gray to 50 gray irradiation. And what I've done in this panel is I've instead of that one-dimensional histogram, I'm looking at it in 2 dimensions so that you can see there's more detail here that we can decode if desired. But the thing that should jump out to all of you at this is that intact molecules in these center panels, after 50 gray of irradiation, almost entirely goes away. So what we're doing is measuring the fragmentation of that molecule. And the corollary to that is we see at the bottom left-hand corner of both of these plots, this is a population of DNA that is chopped up into smaller and smaller pieces. So we can quantify each of these two distributions, and we can measure those distributions. And I can tell you something about the history of that sample as radiation applies to it. And we've recently published a paper on this that is geared toward medically relevant doses. And this just shows that by measuring the dose or exposing DNA, measuring the fraction of the molecules that have been cut into small or double-stranded or have undergone double-strand scission reactions, we can quantify that and we can back calculate the dose from those. We understand the chemistry of this and we understand the physics that's going on behind that. This paper should be coming out on the cover of Analytical Chemistry in the next few weeks. So we're very proud about this work. We think this has direct applications to medical sterilization as well, in part because we can measure the difference between exposures from different radiation sources. So these plots just show the difference between a gamma photon fragmentation pattern from DNA and a proton source. Now you can replace the proton source with an electron source and you get the same kinds of data. The thing that matters here and the thing that matters for sterilization is the different radiation sources require different amounts of or different doses in order to achieve the same result. Now, so far we've calibrated our system up to 20 gray and produced preliminary calibrations for proton beams, gamma, and X-rays. High energy neutrons are under development here, and as well as electron beams. The beauty of this tool is that we can sample from very small regions, and so the total amount of nucleic acid that I need for this measurement is on the order of nanograms. And so simple swabs of surfaces that have been treated for sterilization should be able to be passed into a measurement system with relatively little further development. Of course, the next steps are to extend the doses to ranges important for sterilization. We think we can get up to hundreds of kilogray. We need to add some sterilization sources. So we have not done much work with electron beams, but it's a simple extension. And then we need to connect the molecular damage to the alanine dosimetry reference standards, which are done routinely. And then, of course, to validate with microbial assays as well. And with that, I'm sort of throw this up as a conclusion slide. We think that the biodosimetric approach should offer the data that's needed to support both biological relevance. We think that it can bridge that gap that currently exists between modeling and physical dose. And we think it should offer a path forward toward a molecular-based validation tool for electron beam sterilization and gamma sterilization. I didn't talk much about the instrumentation involved here, but an entire nanopore system like this can be put together for less than $1,000. The current amplifiers that we use in the laboratory run between $5,000 and $10,000, but a purpose-built system that has wide distribution can be made on the scale of a handheld phone, for instance. And with that, I would like to thank the people that I've worked with on this. I've had a number of postdocs and high school students that have done this work. And Eliana Pazos, you may know from this community, has worked closely with me on all of these dosimetry projects. So that is what I wanted to share. Thank you for sticking around.
Thank you very much, Joseph. Unfortunately, we are running a bit over and we have no time for questions, but all your questions will be answered. We will email you the answers to all your questions that have been put in the chat. I would like to thank our presenters for taking the time to be with us and providing their insights in today's topic. And thank you everyone for watching and participating in today's webinar. The recording for this webinar will be circulated shortly, as will the follow-up to the question and answers. Contact information for myself and our presenters will shortly be shown on the screen. and the webinar will be officially ended in a few minutes. Thank you very much again for joining us, and we look forward to seeing you at our next webinar.